We want more cool gadgets. Electronics Unmasked is coming up with a new DIY project to measure speed and acceleration of slot cars. Today it's about a device to measure speed and acceleration on our slot car racetrack. We are not talking about average lap speed now. It's about measuring speed and acceleration at any point on the racetrack. Our slot cars are constantly being improved by swapping motors and the chassis, changing drive gear, improving the tire grip, etc. We are aiming for good top speed, good acceleration and effective braking, and it would be great if we could measure these parameters. Here comes a new DIY project from Electronics Unmasked, and I will briefly explain the principle. Many of you know the physical law from school. It calculates the traveled distance S1 of a uniformly accelerated body, depending on the initial speed v0, the acceleration and the time t1. Sir Isaac Newton found this equation in the 17th century. The plot shows the distance over time. We could measure the time frame t1 that an accelerated vehicle needs to travel the distance s1. From this we could already calculate the average speed. It would be simply the distance s1 divided by the time t1. However, a single measurement is not sufficient to calculate the acceleration. Let's imagine that in addition we measure a time frame t2 that the vehicle needs to cover the distance s2. Then we can apply the equation a second time for s2 and t2. The two distances and the two times are measured relative to the same reference point, which is 0 in our example. Now we rearrange the two formulas so that we get the initial speed v0. We can now eliminate v0 and we can derive the acceleration a from this equation. Next we use the acceleration in the previous formula to calculate the initial speed v0. Using v0 and the acceleration a, we then simply calculate the speeds at t1 and t2, respectively at distances s1 and s2. Next, we take a microprocessor development board to which we connect 3 infrared proximity sensors. We arrange 2 sensors at distances s1 and s2 to a third sensor that represents the reference point. For an initial test, I installed the electronics in a cardboard box, choosing s1 equal to 60 mm and s2 equal to 120 mm. Now let's have a look at the code. First, we need to think about the time resolution we actually need. Our slot cars can travel about 10 meters per second, which corresponds to 36 kilometers per hour. 10 meters per second is equivalent to 10 millimeters per millisecond, which is quite a lot compared to the sensor distances given. In case we could only measure milliseconds, then our accuracy would be unsatisfactory because the measurement error would be about 17% at this speed. Milliseconds measurement was sufficient for our earlier lap counter project, but for the speed measurement we have to measure the time much more precisely. Using an interrupt routine, we are actually able to measure microseconds. We are triggering interrupts via input pins to which the sensors are connected, and then we measure the time between the triggers. This principle is actually simple, but you have to keep a few things in mind when implementing it in practice. We have to prevent multiple triggering of the sensors, and we need a logic that can handle a vehicle covering several sensors. In addition, some further logic is detecting invalid measurements, too slow speed, wrong direction, etc. This is not entirely trivial, as you can see. For my first trials, I simply sent the speed and the acceleration values to the serial interface after each measurement. This way, I can display the readings with the Arduino IDE's serial monitor or a terminal program. I think I will extend this later to Bluetooth, so stay tuned. I'm trying to move my hand in front of the sensors with constant speed, which I can achieve roughly only. These are the measured times in microseconds. Then there are the calculated speeds V0, V1, V2 and the acceleration. The values are making sense so far. We are getting a positive acceleration value when my hand speeds up in front of the sensors. Wow, the acceleration is about 10 times the Earth's gravity acceleration. I was a bit ambitious, as you can see. And then I'm trying to measure a decelerated movement. And here I'm not so ambitious because I don't want to hurt my hand. Okay, that all looks pretty plausible, but can I somehow prove that the values are correct? I struggled a bit on that, but eventually I had the idea to use the acceleration of gravity. Thanks to the famous physicist Galileo Galilei, we know its value of 9.81 meter per second square since hundreds of years. So I put my sensors vertically and then I just dropped this little piece of cardboard in front of the sensors. My measured acceleration is between 8 and 9 meters per second square, which is about 10% lower than the Earth's gravity acceleration. However, this makes perfect sense. The cardboard cannot reach 100% of the gravity acceleration because it is slowed down by the air resistance. So this is corresponding quite well to what you would expect. But okay, so far my test setup is a bit inaccurate and shaky. First, the sensor's measuring cone is getting wider depending on the distance to the sensors. As an effect of this, the trigger point depends a bit on the distance to the sensor. In my first experiments, this might have caused an error of 5 to 10%. Second, my cardboard construction is not particularly precise and the sensors are not exactly perpendicular to the direction of movement. My best guess is that this is causing another 5% measurement error. Third, we assume constant acceleration for our computation, and reality is deviating a bit from that. Anyway, from this test we got important insights that we will take into account for the next step in the project realization. With slightly larger distances and a precise setup, we can certainly achieve a significantly better accuracy. And then I'm thinking about a special housing design, making the measuring cones of the sensors narrow. And the effect that our slot cars are always remaining on the same distance to the sensors will help a lot. I'm eager to see whether in the end our device will be as good as the police speeding cameras. By the way, the police measures speed only and not acceleration. Or do they? Write me in the comments. In any case, we will test the setup on the racetrack and I'm really looking forward to the results. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.